Hello everyone, this is Brock Skaggs. I'm going to make this YouTube video as a kind of a pairing of YouTube videos. The first one here, we're going to go through the calculations in order to design a plate cam, specifically the contours on the outside of the plate cam, in order to achieve a specific follower motion. And then in our second video, we'll basically take that data that we'll develop inside of Excel and we'll throw it into SOLIDWORKS, build ourselves a SOLIDWORKS motion model, and see if we can validate our design. And so first off, what do we want this follower to do? Well, that's what's showing right here on the slide. You can see the prescribed follower motion. I've got 4 different steps or intervals that I want to happen as far as the motion of the follower. This follower is just going to be translating one-dimensional motion, if you will, but I want it to start at some default or reference datum, if you will, and I want it, as soon as the cam to start to rotate, I want it to rise by 1 inch in 0.75 seconds. After it's risen to that 1 inch value, I want it to dwell for 0.5 seconds, remain constant, and then I want it to fall back down to the reference, so I'm falling 1 inch in another 0.75 seconds, then finally dwell a half second, and then if I kept the cam rotating continuously, I would just repeat this process over and over again. Some information that it will need to develop the actual profile of the cam itself will be the type of follower, and so I've already mentioned this is just a translating one-dimensional motion follower. It's a knife edge follower as far as the geometry itself, and then also we need this base circle radius here for some of the equations we'll find in our reference, and that base circle radius is describing how big, really, it's a relative sizing of the cam itself there. And so one thing before I get too far into this, I'd like to point out the reference I'm using. It's a text by Mizeka, Machines and Mechanisms Applied Kinematic Analysis there. We're using it currently for the 420 Kinematics class. And if you want further details on this process and be able to deal with other applications other than just a knife edge follower, for instance, go ahead and grab a copy of that reference there. We are in chapter 9 is where you'll find the information about cam design. And so one thing I've done to speed up this process a little bit is to go ahead and start a Excel spreadsheet so we can start organizing our data. And so that's what you're seeing before us, and we'll work through this. And so I basically got everything copied from that initial slide and then kind of a template laid out with some calculations we'll run through. And so one of the first things we have to do is figure out the angular velocity of the cam. And so we've got a easy relationship here that's showing how to get that value. And so omega of the cam, its angular velocity, 1 revolution over the sum of the time intervals. And so what we have here is the idea that we have 4 time intervals, 4 steps, if you will, that the follower is going to go through in this example, and we're going to sum the time required for each one of those steps and take that as the denominator in this fraction. And so the idea is we want, during 1 revolution of the cam, all 4 of these events to happen, if you will. And so I've got it worked out right there on the slide. We'll do it here as well. I'll say sum of time intervals just so we can put this off on a cell. And we'll put this right here. 0.75 seconds is the amount of time it takes for the first rise, half second for the dwell, another 0.75 seconds for the fall, another half second for the last dwell. So it looks like it will take in total 2.5 seconds for this sequence of motion intervals to happen. And so here, just straight from the book, 1 over the sum of the time intervals gets us the angular velocity of the cam. In this case, 0.4 revs per second. More convenient unit, especially when we go to SOLIDWORKS, would be RPMs, and so I will just multiply that by 60, 24 RPMs, and then a convenient unit in case we have to use this at all in any of the calculations down below in our table would be radians per second. And so here, 1 revolution is 2 pi radians. And so that relationship there gets us to 2.51 roughly radians per second. And so now we're really ready to get down into the meat and taters, if you will, of this calculation. And so first thing I need to do is think of starting time at t equals 0 when I first start to rotate the cam. And so as I first start to rotate the cam, this is also when the follower is first starting its harmonic rise, right there at the very beginning. Well, I need to basically decide on a time step that I need to be able to walk my way through the motion of the cam and motion of the follower. And so here I'm going to pick a pretty small time step, 5 thousandths of a second, and basically use column A to work myself through. And as you can see, as I pull this down, I will just be increasing the value of the cell below the cell I'm talking about by 5 thousandths of a second. And I need to drag this down all the way until I get to 2.5 seconds. This is how long we said it was going to take for this cam to rotate through one revolution and have all of our motion steps. So it really goes quite a way. As you can see, we're on row 523 for 2.5 seconds, and then this all starts on row 23 at time equals 0. Of course, in Excel, it's not really too much more work to make a step size that large than a step size of a half a second. But in this case, I need pretty fine steps in there to make sure my cam profile works out well, so that everything is going to be nice and smooth and I don't have real jagged edges or anything like that on the cam. So next we're basically going to work our way left to right in this table. Cam angle. And so this is basically talking about the angular position of the cam as we walk through this motion. And so our cam is spinning it at a constant angular velocity, 24 RPMs, or in this case, since I'm trying to figure out a cam angle with units of radians, I'm really thinking of the 2.51 radians per second. And so simple constant acceleration formulas come to mind from the beginning of the semester. I can think of theta equals theta naught plus omega naught t plus 1/2 alpha t squared, if you will. So this one, it's constant angular velocity, so there's no accelerations. The angular velocity is this right here, and so it would be this times this. Basically talking about taking the speed at which it is spinning times the time that it's been spinning. That would give us how far it is spun, if you will. The only short modification here is we need to lock cell B18 to make sure we don't drag that down with A23. And I'll just evaluate down through our table. Next, just for convenience, I've got degrees in here, and so I'll just call the degrees function inside of Excel to convert those angles from radians to degrees, just because I can visualize about 5 degrees much better than I can visualize 0.09 radians there. And so we're going right along here. One thing that I would like to check is to make sure that we go through one revolution during these 2.5 seconds. And so I'm starting at 0, and so at the very bottom of these should be roughly 2 pi here in column B and 360 degrees in column C here. And so I'll just drag us down, and you can see there in column C, 360, that is right about 2 pi there, 6.28 and change for the angle in radians. So that is one revolution. So now for the follower characteristics, which is columns D through F there. And so notice at this point we are totally independent of the cam profile itself here. Here we're just going to be trying to describe the motion of the follower. And this is largely stuff that we're given through the design input here. And so how do we go about doing that? Well, first we could look at the original design inputs in the PDF here. I want a harmonic rise 1 inch in 0.75 seconds. That's the first motion interval. What does that mean? Well, I'm going to essentially start at 0, 0, where I'm at a height of 0 and time equals 0. And then by the time I get to a time of 0.75 seconds, I need to have risen by that 1 inch. But what happens in between there? I've basically described 2 points, but how do I connect the points? That's where this harmonic rise is going to come through. There's different motion schemes that are shown in the reference text, and so one of those is the harmonic motion. And so on page 231 of our reference, you can see I've got a few figures here, and then also there are tables describing the curves on those figures. And so here's the table and the associated figure. What you'll see in both the tables and the figures is that they're broken off in terms of rises and falls. And so here, for my first one on the rise, I only want to look at the left-hand side of this table and not the right-hand side. But you see a bunch of different variables in here. What do they all mean? Well, that's where the figure comes into play. And so, for instance, for this rise, the h sub 0 is the initial height. For us, we're starting with this very first step, and so that'll just be a 0 value for us. The h sub I, that's the amount that we're going to rise. And so in our first one, we said we were going to rise 1 inch, so that's going to be 1. The capital T sub I is right here. And notice this is the amount of time it takes for this interval to happen. And so in this case, it'll be 0.75 seconds. And then the lowercase ti, you can see down here, is basically the independent variable marching along this time interval there. And so lowercase t sub I is always going to start at 0 when you start the motion interval, and then it's going to walk with your step size all the way up till it equals capital T sub I, and that means your motion interval is going to be done there. Another way of looking at this is through, instead of being time driven, as it can be driven by the rotation of the cam itself here. This is the way I usually don't look at it. I'm more tuned to looking at time than rotation angle of the cam, but you can do it. The only differences you make is instead of looking at T sub I, you look at it beta sub I, and beta sub I there is the amount the cam is going to rotate during that motion interval, and phi sub I is essentially the lowercase t sub I, except for you're looking at a step in terms of angular displacement instead of a time value. And so you'll see that in all of these equations. You'll have a first equation with time as the driving variable, and then the second equation underneath it is the angle as the driving variable. Again, I don't like doing the angle way. I'm more driven toward time, and so I'm going to use the time ones here. And so with that being said, I think we are now ready to run this equation here. And so here we talked about h sub 0 being 0. I've got h sub I is 1, so it starts off 1 over 2. And I'll be entering this right here. So 1 over 2 times parentheses 1 minus cosine. I've got pi times t sub I. This is the lowercase t sub I. In this case, since it's my very first motion interval, I can just set that equal to the global time step there. You'll see that when we go to other intervals, that'll have to be changed. And so then I'm dividing that by capital T sub I. That's the amount of time this interval is going to take, so 0.75 seconds. And that gets me to the follower displacement. Okay, sorry about that. Had a small interruption, but I think we are back online now, looking at just calculating the follower displacement there. And so we've got the formula entered in there, and now we need to do a similar thing for the follower velocity and acceleration here. And so really the same process at this point, looking down here to the velocity expressions and the acceleration expression there. And so I'll just quickly enter those in. I'll try to toggle back and forth here. So pi over h sub I divided by 2t sub I. So pi times h sub I. H sub I was the amount that we're rising, so that's 1. Divided by 2 times t sub I, that's 0.75 there. And so that was then going to be multiplied by a trig function, it looks like, times sine. So I've got pi times the lowercase t sub I. And so again, since this is the very first motion interval, I can just reference the global time step there, and then divide that by capital Ti, that's the amount of time for the motion interval, 0.75. And here I'm expecting that value to start, yes, very close to 0. And now for our acceleration. And so the acceleration expression, I'm looking now right down here, pi squared h sub I over 2 capital T sub I squared. So there's my pi squared times the h sub I is 1 divided by 2 times t sub I squared. So that'd be 0.75 for this case. All right. So moving right along here. And I believe it's times now the cosine. Pi times the lowercase t sub I, so that's our little step inside of the motion interval, and divide that by the 0.75, the length of time for this motion interval to take. Alright, so now I've got expressions loaded in to describe the follower displacement, velocity, and acceleration during the harmonic rise that's going to last between 0 and 0.75 seconds. And so notice here it's going to stop at 0.75 seconds. So I need to now drag these equations down until I hit 0.75 seconds. So right there. And so notice here the displacement was in column D, so it's going to 1. And I've got velocity in column E and acceleration in column F. And so one thing I like to do is shade these. So that way when I'm coming back to look at it, I can clearly see where the motion intervals are starting and stopping. And so we've described the first motion. What happens after this harmonic rise? Well, we dwell, right? We dwell for 0.5 seconds. And so this is an easy one. When we dwell, the displacement is going to remain constant, right? This follower is not going to be rising or dropping during this time, so it'll just remain at 1. If the displacement or the position of the follower is remaining constant, the velocity is just a derivative of that with respect to time, so it's got to be a 0. And then acceleration is a derivative of velocity, so it's also going to be 0. And so in this case, it'll be 1, 0, 0. And this dwell lasts from 0.75 to 0.75 plus the half-inch duration, or to 1.25. And so here I'll just select and bring it down till 1.25 seconds. And so almost there. Here's our 1.25 seconds. Very good. And I'll save this. And so now we're at 1.25 seconds. Basically, we've risen, we've dwelled. Now we're ready to fall back down to the original values, is what we wanted our motion to do. And so in this case, we're on a fall instead of a rise. And so we go back to our harmonic motion equations. And so instead of the left-hand side, now we're looking at the right-hand side. And notice the equations for displacement, velocity, and acceleration are similar, but just slightly different than the equations we've been dealing with before. And so I'll be entering in these equations in order to describe the fall. As far as h sub f and h sub j, you can just look at the figure here. H sub j is the amount of the fall. H sub f is the final height. And so, for instance, on this first displacement, h sub f, that's just going to be 0, right? We're getting back down to that reference datum. H sub j is 1, and so it'll be a half times 1 plus cosine, and then we get into the argument that we'll have to look at. And so here, it's equal to 1/2 times 1 plus the cosine of pi times. Now we have something a little bit different. Right here, we're 1 over 2 times 1 plus the cosine of pi times t sub j. Before, with t sub a, we just referenced the global time step over here in column A. But now we've got to think, okay, I've got to reset this time step inside the motion interval. So this value here, instead of needing to be 1.255, it needs to be 0.005, right? Because we're only 5,000ths of a second into this motion interval. Easy way to do that, though, is again reference the global time step, 1.255, but then we'll subtract off the initial time of this motion interval starting. So that's 1.25 in the global sense. And so that will now basically transform this into the lowercase t that I need. After making that change, I just have to divide by t sub j to complete the formula. That's 0.75. Couple parentheses there. And notice this very first value is just slightly under 1, which is what I would expect. And let's go ahead and drag this down to what would be 2 seconds in this case, in order for us to see if this works for that slight modification with the lowercase t sub I. There we go, dragging down to 2 seconds, and notice we've got all the way down to 0. And just like before, I'll do some shading here so I can see where that's at. Good. So for the rest, column E was velocity and column F was acceleration of the follower. Here I'd really just be entering in this expression here and this expression here as well. Instead of taking the time on YouTube to do that, I'll go ahead and go to some calculations I've already done that should work for us. I'm basically starting right here, and I'll copy these ranges in. And so this will just shorten the video a little bit. Sorry, the video is already going to be a little longer than I'd like. Just like so. And notice here on both of these, I'm making the same adjustment for the lowercase t sub I. You can see it right there in the velocity. And so at this point, I've risen, I've dwelled, I've fallen, and the last thing was to dwell again for a half second. And so for dwelling, the displacement's going to remain the same, so that'll be 0. If displacement's constant, well, velocity has to be 0, and then if velocity is a constant, in this case 0, acceleration has to be 0 as well. And so these will populate through the end of my table. And so at this point, I have described the follower displacement, velocity, and acceleration. Let's go ahead and just create a couple graphs just so we can see what we've created at this point and visually inspect it before we move on. And so I'll add a XY scatter plot. There we go. The X values are going to be the times. The Y values will be displacement. And so just getting those highlighted. And now you can see I've got the follower displacement, is what we'll call this. There we are. And so this looks pretty good, right? We start at 0, we rise to 1 inch in what looks like 0.75 seconds. I dwell for a half second, that's right about 1.25. And then I drop down to 2, or excuse me, drop down to 0 by the time I get to 2. And then I'm dwelling out my last half second. So that looks pretty good. Let's also look at the follower velocity. And so here, just playing around with the references, there's the follower velocity. Notice you only have velocities that are non-zero during the rises and the falls, right? Not during the dwells, so that's looking good. And then finally, acceleration. And so here's follower acceleration, and we'll again reference this right here. And so again, that's looking quite well. One thing you can see, a little bit of guidance on how these curves should look. Right in the figure, you can see with a harmonic rise, you have this is the general shape for the velocity, acceleration, as well as displacement. Same thing on the fall, and those should match up what we're doing in this worksheet here. And so at this point, basically what we've done is in very good detail here described the motion of the follower. But again, this whole thing was to figure out, well, what's the cam got to look like in order to achieve this? Well, that's what these Rx and Ry columns are going to be for. In the textbook, in the reference here, specifically section 9.9 is what I'm looking at. There are relationships or equations that relate things like, in this case, for the knife edge follower, the base circle radius and the displacement of the follower, as well as the cam rotation position of the cam, excuse me, and give us the appropriate coordinates. And so Rx and Ry, think of these as ordered pairs, which are basically going to outline the cam profile in an XY plane. And so you have to know a little bit more information about the cam and follower geometry, for instance. There's different equations, different relationships for a knife edge versus an inline roller follower, translations versus pivoting followers, and so forth there. And so this is where it starts to get a little bit more important to know what the geometry looks like. For the knife edge follower, it's quite simple as far as these relationships goes for Rx and Ry. It is the sum of the base circle radius and the follower displacement for Rx, and we're multiplying that by the sine of the cam angle. This needs to be in radians, and so I'm referencing that value. And so just evaluate that down. And then for the R sub y, it is again the sum of the base circle radius and the follower displacement. This time we're multiplying by the cosine of the cam angle. And here I forgot to lock B12 there. So I need to lock B12 so that that stays on there, and do a similar thing in this one. There we go. So now let's see what this cam is going to look like. And so here I'll just copy and paste. The X needs to be for R sub X. The Y needs to be R sub Y. And there we have it. This is no longer follower displacement, but this is the cam profile. And so what this is a plot. Here I'll just go ahead and move it to a chart sheet so we can blow it up a little bit. There we go. This is a plot now of the contour of the cam, or the cam profile. And so the idea is if I create a cam that looks like this, and I rotate it about an axis that's running perpendicular to the screen right now and right at the origin, 0, 0, and I have to rotate this at a certain angular velocity, 24 RPMs with a knife edge follower, then I will create this type of motion that you're seeing here with the follower. And so that's where we'll quit at this video. This video we've basically created the cam profile. With doing that I was creating the X and Y points, X and Y data points if you will, for the contour that we run along here as we look at the cam. And in my second follow-on video, we'll take this data from Excel, move it into SolidWorks, and then use SolidWorks Motion to validate this. And so thank you for watching this video. Hopefully it helps you out with your cam investigations, and be sure to watch the second one to see the SolidWorks Motion part of it. Thank you again.